Hello there, Mr. Sutton here, bringing you the IM372 Extra Practice Number 4 solutions on special right triangles. For this roundabout problem, we have a circle with center O, and I know this kind of looks like the symbol for the Deathly Hallows from Harry Potter, but just roll with it. We have an area for this circle of 9 pi. We want the area of the equilateral triangle that's involved in this. All right, so just kind of planning ahead here. To get the area of this triangle, we need to figure out the base and the height, so we can do 1/2 base times height. In fact, let me start by actually labeling the height and the base of that triangle so we can find those in a minute. And in order to get any of these, we have to relate it back to the circle. The only measurement we have is the area of this circle. Now, that area, we can actually use that to work backwards and find this height, because the height of this equilateral triangle happens to be the diameter of the circle. And although we don't have a formula that directly relates diameter and area of a circle, we do have a formula for the area of a circle in terms of the radius. We have area equals pi r squared. So if we can figure out the radius, we can double that to get the diameter, which will give us the height of the triangle. All right, so for area, we have 9 pi. So we can write 9 pi equals pi r squared. Dividing both sides by pi, we have 9 equals r squared. So then if we square root that r squared, we have r equals 3. All right, and if I double that, that's going to give me h, so h is going to be 6. So we have a height of 6. That's great, but we still need to find the base. So how can we figure out the base? So at this point, it helps to recognize a few facts. One of them is that this is a right triangle, or this base is at least made up of 2 bases that are parts of right triangles. And because this is a right triangle, and we've actually already got one side of the right triangle, that means we can try to use special right triangles to figure out some other sides. Now, which special right triangles are we dealing with? Well, since this is an equilateral triangle, here we need to know a little bit about equilateral triangles. That means that all the sides and the angles are the same. And since all the angles are the same and you have 180 degrees to work with, that means all the angles are 60 degrees. So we have 60 degrees here, 60 degrees here, 60 degrees up here. Now, for just this little left triangle here, not the big triangle, just the left one, since you've already used up 90 and 60, that means this other angle up here is 30 degrees. So that means we actually have a 30, 60, 90 triangle, which means our sides are going to be in the ratio of s radical 3, and 2s. In fact, let me go ahead and label the sides of that left triangle with those s's. So just one s, that's going to be across from 30. S radical 3 is across from the 60 degrees. That's this whole side here, which is the height. And then 2s, that's the hypotenuse of that triangle. Now, the only number that we actually have on this triangle is this h. We found that that was 6 back here. So we can say that s radical 3 equals that 6, that h value. To find s, we just have to divide both sides by radical 3. So that's going to be 6 over radical 3. And if I multiply by radical 3 over itself, that's going to be 6 radical 3 over 3, which is going to be 2 radical 3. So that's this side down here. Now, the base of that whole triangle is going to be 2 of those. So 2 times 2 radical 3, which is going to give us 4 radical 3. All right, so it took a while, but we've got the height and the base of the equilateral triangle. Now we just use 1/2 base times height to put it all together. So we have 1/2 times our base of 4 radical 3 times our height that we found way back when of 6. So half of 4 radical 3 is 2 radical 3. 2 radical 3 times 6 is 12 radical 3. And 12 radical 3 is choice C. On this open response problem, designed to test our knowledge of geometry, we have a diagram with rhombus ABCD, and we have a side length of 8 centimeters. We're also told that the measure of angle ABC, that's this top angle here, is 60 degrees. First question, first part, we want to know the perimeter in centimeters of the rhombus. Well, the key here is recognizing that with a rhombus, what it means to be a rhombus is that you are a rectangle where all the sides are equal. So if all the sides are congruent or equal in a rhombus, That means that you have 4 of these 8 centimeter sides. So that means the perimeter, if you add up all the sides, is going to be 4 times 8, which ends up being 32 centimeters. For this part of the problem, they want the length in centimeters of diagonal AC, this diagonal right here. In order to get this, we're going to first find the length of just this little part of the diagonal here, and then we're going to double that. Because this is a rhombus, we know a few important facts. One of them is that these diagonals, or at least the long diagonal, bisects the short diagonal. So we know that if we find this piece of it, doubling it will give us the whole thing. Some other facts we know. We know that the long diagonal bisects these angles at the ends here. That means that this angle up here, which they told us in the beginning was 60 degrees, we're cutting that in half, so we actually have 2 30-degree angles in each of these little quarter triangles. So this is actually 30 degrees right here. And because we know that the diagonals in a rhombus are perpendicular, that means that this is 90 degrees here, and then this is going to have to be 60 over here. So knowing all of that about a rhombus tells us that we've actually got ourselves a 30, 60, 90 triangle right here. Okay, so that means that our sides are in the ratio of s, s radical 3, and 2s. And if we label those sides of that little upper left triangle, s is across from 30, s radical 3 is across from 60, and 2s corresponds to this 8 centimeter side. In order to figure out this AC side, I need to first find the value of s. But I don't know s. I do know that 2s is the same as 8 centimeters. So I can write 2s equals 8. That means if I divide by 2, that s equals 4. And then to get AC, that's going to be 2 times 4, 2 times s. So that's going to end up giving us, well, 8. It's funny how that works out. For this part of the problem, we want the length of diagonal BD. So a crucial part of this is that we already figured out that this little s value that we set up with our 30, 60, 90 triangle, that s value was 4 centimeters. That was from part B that we found that. So we're going to use that to help us out here. Now, in order to get diagonal BD, if I could at least figure out what this s radical 3 side of this upper left right triangle is, I could double that to get BD. Well, we already know that s is 4 from part B. So that means that this is going to be 4 radical 3. So in general, BD is going to be 2 times the s radical 3 expression. So that's going to be 2 times 4 radical 3, which means BD is going to be 8 radical 3, and that is still in centimeters. For this last part of the problem, they want the area of the whole rhombus. The way I'm going to do this is I'm going to figure out the areas of 2 triangles that make up the rhombus and add those 2 triangle areas together. So each of these triangles has an area of 1/2 base times height. I just need to find the base and the height for each of them. So the 2 triangles I'm going to use this left big triangle here, ADB, and this right big triangle, BDC. So for the left one here, we've got a height of 4. That's kind of the altitude from, I guess this is the top to the bottom, one way of thinking about it anyway. And then we also have a base, that's this long side here, BD. We found that in another part of the problem. That was 8 radical 3. So we've already figured out these 2 values in past parts of the problem. I mean, if we've already got it, let's reuse it, right? So base times height then, that's going to be 1/2 times 8 radical 3 times 4. Well, that's 4 radical 3 times 4, which is 16 radical 3. So that's the area of this left half of the rhombus. To get the area of the whole rhombus, I just have to double that. So that's going to be 2 times 16 radical 3, so 32 radical 3. Don't forget our units of square centimeters. On this problem, we have this circle with a square inscribed inside of it, and we're told the diameter of the circle is 20 inches. So our first part of the problem, we want to know the length of segment TP, this little side right in here. So the key on this one is they gave us the diameter of the circle. They said it was 20 inches. That means that MP, the diameter of the circle, one diameter anyway, which also happens to be a diagonal of the square, MP has a length of 20 because it's a diameter. TP is going to be half of that. And we know it's half of that because with a square, the diagonals bisect each other. because a square is a type of rhombus, and in a rhombus, the diagonals bisect each other. So that means TP is half of that 20, which is going to be 10, and that is in units of inches. For this part of the problem, they want to know the measure of angle QTP. Now, the fast way of doing this is if you just happen to know that a square, which this is part of, a square's diagonals are perpendicular, then you would know automatically that this was 90 degrees. That is just one of the properties of a square. It's actually a rhombus property, but a square is a type of rhombus. But there's a way to take kind of the long way around. So we have 4 triangles here, and in all these triangles, they're all made up of the radii, which we know all the radii are the same because the radius of a circle doesn't change, and they're all made up of the sides of the squares, which are also all the same. Since our triangles are formed by the radii and the square sides, and all those are congruent with each other, that means that all of our triangles are going to be congruent. They're all the same triangle, just oriented in different directions. That means that all these T angles are also going to be the same. Well, since there's 4 of them, and we have 360 degrees to go around, 360 divided by 4 is going to give us 90. So that's another way of getting to 90 degrees. But again, if you knew that the square's diagonals were perpendicular, that was kind of the fast way there, if you explained it that way. On this part of the problem, they want to know the measure of angle TQP. That's this angle down here. So we already established that this T angle up here was a right angle. And we already know that these 2 sides of the triangle are congruent because they're both radii of the same circle. So you've got 2 sides that are the same. You've got a right angle. You've basically got a right isosceles triangle. In a right isosceles triangle, you've used up 90 degrees here. That means these other 2 angles, since it's isosceles, these 2 angles must be exactly the same. So they're both going to have to be 45 degrees. So we know that right isosceles triangles are always 45, 45, 90 triangles. We also know that the 45-degree sides are going to be across from the legs of that isosceles triangle. So that means that since TQP is across from one of the legs, it must be the 45-degree angle, one of those 2 45-degree angles. For the last part of this problem, they want the length of segment QP down here. So just to review what we've already established in past parts of the problem, we saw that this angle was 45. That was part C. That means this angle's got to be 45 because we established in part B that this angle up here was 90. So this is a 45, 45, 90 triangle. That tells us that the sides are in the ratio of S, S, and S radical 2. So we've got S across from 45, S across from the other 45, and across from 90. That's the S radical 2 side. Now we need one side of this triangle, and then we can find all 3 sides, or at least the other 2 sides if you already have one side. Now the key side here we found in part A. It was this TP side. Remember, we found that that was 10 back in part A. So that means that S and 10 are the same thing in this situation. Now since QP is really S radical 2, that means QP has a length of 10 radical 2, which is going to be 10 radical 2 inches to match the units there.